Hello everyone, my name is Mwamba Kasongo. I'm a PhD student in the Department of Computer Science at University in Seoul campus. And today I'm going to present my presentation about Bayesian optimization technique for hyperparameter tuning. So this study focuses on leveraging Bayesian-based optimization techniques to intelligently navigate the hyperparameter space, aiming to navigate, and this study focuses on leveraging Bayesian-based optimization technique to intelligently navigate the hyperparameter space, aiming to enhance the efficiency and effectiveness of hyperparameter tuning for image classification. Our presentation is about Bayesian-based hyperparameter tuning for classification image. The outline is as follows. 1. Why HPO? 2. The proposed Bayesian HPO for visual transformer architecture. 3. HPO techniques. 4. Methodology of Bayesian HPO approach. 5. Experimental result. 6. Transformer vision models. And 7. I'm going to give our conclusion. Machine learning typically involves several steps which can be summarized as follows. The first step is the problem definition, where we clearly define the problem we want to solve. First, we need to do the data collection. We gather and collect relevant data for our problem. The next important step is data preprocessing, where we clean and preprocess the data to make it stable for machine learning. We need to prepare data for machine learning. We need to prepare data for machine learning by splitting the data into two subsets, typically a training set and a test set. Then we select a machine learning model for our problem. Next, we train the model, which means feeding the model with input data, adjusting its parameters to learn patterns and make predictions. Transformer vision is a neural network architecture that extends the idea of transformer architecture from natural language processing (NLP) to computer vision tasks. Here are some important hyperparameters to consider when working with transformer models, such as learning rate, weight decay, and number of neurons. HPO is a crucial step in training machine learning model to achieve better performance. Hyperparameters are parameters that are not learned from the data but are set before training. Therefore, optimizing this parameter can significantly affect the performance of the model. And here are some popular HPO algorithms, such as the grid search, the manual search, random search, Bayesian optimization, and genetic algorithm. Bayesian HPO is a powerful technique for tuning the hyperparameter of machine and deep learning models. And HPO is described in equation form as x equal to argmin f of x. And here, f of x represents a function to minimize. X star is the set of hyperparameters that yield the lowest value of the score. And x can take any value in the domain x. Here are the key components and steps involved in Bayesian HPO. We have a domain, a basic function, the surrogate model, the acquisition function, and a story. A classification data set is a collection of labeled images that are used to train machine and deep learning models to recognize and classify objects. Here we have used 3 image data sets: the CFAR, which has 10 classes, satellite image data set, which has 4 classes, and the CFAR 100 data set, which has 100 classes. We now define the stitch space for our hyperparameter for basic function. This includes specifying the range or possible values for each hyperparameter that we want to optimize. The stitch space can be continuous, discrete, or mixed. When running the Bayesian HPO algorithm, we must define the initial points. Bayesian HPO typically starts with an initial set of hyperparameters randomly selected or based on prior knowledge. In our study, we have defined 5 values of 5 initial points: the units or neuron in the hidden layer, the learning rate, the weight decay, the activation function, and the drop rate. And these initial points are used to build the surrogate model. The result is from the deep learning model training process. The training process has gone through 50 epochs, and the model achieved an accuracy of 77%, which means it's correctly classifying 77% of the training set. In this case, the loss value is 0.91, which means on average, the model predictions are deviating from the true value by approximately 0.91 units. When we perform Bayesian HPO using GPy library, the first result we typically obtain is the optimal set of hyperparameters. This set of hyperparameters corresponds to the configuration that is expected to yield the best performance according to the surrogate model used by the Bayesian optimization. After 6 iterations, the Bayesian algorithm gives us the optimized parameters. The result is from the deep learning model training process on C400 datasets. The model has achieved an accuracy of 53% after 50 epochs, while the loss value is 3.16. This is the result of the Bayesian HPO algorithm on C400 datasets. After 6 iterations, the Bayesian algorithm gives us the optimized hyperparameters compared to the result obtained on C410. The optimum learning rate is 0.0001 when trained on C400 and 0.00001 when trained on C410. On satellite image datasets, the model has achieved an accuracy of 93%, which means it is correctly classifying 93% of the training set, while the loss value is 0.33. After training and evaluating the Bayesian HPO algorithm, we obtain the optimized hyperparameters that correspond to the best performance according to the surrogate model. Then we use those optimized hyperparameters to train the Bayesian transformer encoder for image classification task. Now, let us compare the result for the different datasets. Considering the accuracies, C410 achieved a slightly lower accuracy at 92% as described in the figure, showing a strong performance in classifying 10 classes of images, while C400 had the lowest accuracy at 77%, which suggests that classifying 100 classes is more challenging task for the model. Satellite dataset achieved the highest accuracy at 97%. Satellite dataset achieved the highest accuracy at 97%, indicating excellent performance in classifying satellite images. Moreover, satellite image dataset had the lowest loss at 0.09, indicating a highly efficient model in terms of training and convergence. Then the C410 had a higher loss at 0.83, implying a relatively higher training loss compared to satellite image dataset. Satellite image datasets show super performance in both accuracy and loss, suggesting the effectiveness of the model in classifying satellite images. In conclusion, Bayesian optimization can be used effectively for hyperparameter tuning in image classification tasks. When applied to image classification, Bayesian optimization aims to find the best set of hyperparameters for a machine and deep learning model, such as the transformer vision or a CNN model, to achieve optimal classification in performance. Bayesian optimization is especially valuable in scenarios where evaluating the performance of a model is computationally expensive or time-consuming, such as training a deep neural network on large image datasets. And it efficiently explores the hyperparameter space and can lead to significant improvement in image classification accuracy. And this is the end of the presentation. Thank you for listening.